Let's spend some time over the next couple sections looking at basic Linux skills that apply regardless of distribution. So we're talking about shell utilities, useful utilities that you use invariably to navigate the Linux landscape. So let's open a shell, get our gedit notes going, and we'll label this section Basic Linux Skills, which will split over two sections. So the features of these particular utilities is that, one, it includes, but not of course, not limited to, useful utilities that when combined can perform powerful actions. And this, of course, this is the entire premise of Unix, thus Linux, and that is a number of small utilities that, when aggregated using mechanisms such as pipes, as well as input and output redirection, can come together to perform larger tasks to which the individual utilities excel at. So what we'll do is look at each of these utilities and try to get through them rather quickly, as we'll be using them throughout our studies, and you should be using them throughout your time with Linux and Nix-based systems. Now, most, if not all, Linux distributions include a version, a GNU version in particular, from the Free Software Foundation of the utilities that we'll be using. Some Unix distributions like Solaris and FreeBSD, for example, include most but not all of the utilities, or in some cases all of the utilities, but with variations with respect to capabilities. So you'll have to check the help for the counterparts on other distros like FreeBSD, Solaris, AIX, HP Unix, and otherwise. But within the Linux realm, these utilities are the GNU versions of them. And the good news is that these GNU utilities can be compiled, and you may also find binary versions of the packages for other distributions of Unix, such as HP Unix, IBM AIX, so on and so forth. So you can replace system utilities with GNU versions. So let's just note as another feature that these are GNU, Free Software Foundation utilities. And it's these utilities that comprise largely the GNU Linux system. Linux is the kernel. The utilities, which make up the overwhelming majority of the operating system, comprise the operating system. So what are some of those utilities? In no particular order, let's just note as a task, explore utilities. And let's change the nomenclature slightly so that the task is listed with an alphabet and the utilities are indicated numerically, since there are far more utilities than the alphabet allows. So for example, when you open a shell, it's a good idea to know who you are, the context within which you're connected to the system. All the utilities we'll mention will be specified between single quotes. Who am I can be found on virtually all Unix, Linux-based systems. So this utility reveals currently logged in user. And this is per shell. So if you open two shells, one with the user, let's say LCBT, the other with the user root, who am I will reflect those differences. So let's take a look from the shell perspective. So Control-Shift-T gives us a new GNOME terminal shell. A which is one of the important commands, who am I, tells us it's in user bin. Utilities that are beneath user bin, as well as /bin, are accessible to all users of the system, both privileged and non-privileged users. Whereas utilities that are beneath sbin, such as /sbin or /user/sbin, are reserved for privileged users. It doesn't mean that non-privileged users are unable to execute those utilities. They're just out of the path by default. And in some cases, the non-privileged user cannot execute the utilities. So, who am I tells us that we're logged in as user LCBT. Now, one of the neat things about GNU Linux, regardless of incarnation, so regardless of distribution, is that the currently logged in user is represented on the shell in the prompt. So this is a feature provided by the bash shell. So we already have that information without having to run who am I. So for example, This is the bash shell prompt, and it is variabilized to include user at host, and this is the short host name of our system. In fact, if we navigate to the shell and execute hostname, you'll see it returns this particular hostname, Linux CBT Deb1, whereas hostname-f returns the fqdn. And we're just rattling off commands, so let's just include hostname as well. So the bash shell prompt incorporates user at host, where host is the short host name. And we can reveal that with another command, and that is hostname. This reveals the name of the host as configured in etc hosts and otherwise. Sometimes the system's host is defined in multiple files. In Linux, you can find the host name in etc hosts. You should see a reference in there including both the fqdn as well as the short name for the host at the loopback adapter's address at the very least. Now, because this system connects using DHCP, its IP address isn't in the hosts file, but could be updated by the DHCP client if required or if configured accordingly. So hostname reveals the host, and a variation on that, of course, that's useful is hostname-f, which reveals the fqdn of the host. We'll just indicate host, which begs the question, is there such a variable named host? Well, in this case, we see that there isn't a variable named host set. How about hostname? Hostname is actually set, so that variable is in place. Which brings us to another command, and we can go on with these different incarnations, but echo is a useful command across operating systems. It echoes whatever you tell it to, including variables. So dumps literal or variabilized data to stdout, standard out, which is the screen. So echo is quite useful because we can use it along with variables, and we'll lean on it quite often. So who am I? Hostname echo. Another useful command is su. This switches the user's context. So switches user's context. So normally when you use your Linux system, you're logged in as a non-privileged user. But supposing you wanted to, for let's say, a particular task, access the system as root. So let's Control-Shift-T in another shell, and we'll su in. By default, when you don't indicate a particular username, su will attempt to connect you to the system as root. So let's indicate root's password, and so long as we're successful in including root's password, notice that the prompt is updated. So by default, su switches context to the user root. So for example, this is the root shell. Root shell. And by the way, there is a variable named shell. So when you su in by default, it switches to the context of root. So switches user's context and defaults to user root if unspecified, which means you can su to other users if you'd like. So for example, you may need to check someone else's mail or perform a task as someone else because of permissions restrictions, which would cause you to use, for example, su space the user's name. So for example, su Linux CBT will switch to the context. So switches to the context of user Linux CBT. Another thing that you should know about su if you're unfamiliar is that by default, if you're logged in as root, as we currently are in this particular shell, by the way, who am I tells us now that we're in as root, and notice that the prompt differs from when logged in as a non-privileged user. As a non-privileged user, it terminates with the $ symbol. As a privileged user root, it terminates with the hash mark or the number sign. So that's a visual way you can tell the differences between the logged in users. Now, when logged in as a user root, you can su in as any user on the system without being prompted for authentication under the standard discretionary access control configuration of Linux, meaning if you haven't implemented a technology such as SE Linux, for example, a Mac-based mandatory access control, or some other access control system. So under normal circumstances, when you're logged in as root and you su as, let's say, user Linux CBT, automatically root has that privilege to switch context to the user Linux CBT. And notice that bash reflects the change by updating the prompt accordingly. So now it's user Linux CBT at the short name of the host. And we are indeed back in as user. And now when we execute W, we see a number of sessions happening. Also notice that when we execute W, we see sessions on TTY as well as PTS. The PTSs reflect pseudo terminals that are automatically generated by the GNOME terminal. Let's just copy this output into memory, as we've yet included another command into the fold. So the W command, as we've mentioned earlier, reveals currently logged in users and their shells or terminals is the better term. So for example, here's an output of a recent W execution. Notice that on TTY7 is the X session manager. TTY7 is the placeholder for GNOME terminal or for the GDE environment, whereas GNOME terminals are open on these pseudo terminals, PTSs. So on TTY7, the X session manager is managing this current graphical environment that we're taking advantage of. And it's under the auspices of the user Linux CBT. That makes sense because we logged in as the user Linux CBT. In fact, if we attempt to log out, we see that it reads logout username or logout Linux CBT, which would kill this instance of the X session manager that's bound to the user Linux CBT. Additionally, we see 3 pseudo terminals. PTS is a shortcut or an abbreviation for pseudo terminals. So let's just note that as well. Note, PTS means pseudo or phony terminal. And the pseudo terminals are, let's just note, these are dynamically generated as needed by the GUI terminal software, rather than restricting it to simply GNOME terminal, because it could be KTerminal, KDE terminal, or any other window manager's terminal. So PTS as a prefix means it's a pseudo terminal. It isn't an actual physical terminal that's accessible via Control-Alt F1 through F6, for example. These are terminals that are created on the fly, instantiated on the fly as we open new GNOME terminal windows and tabs. So for each one, they're seated at 0, and they increment accordingly. So currently, if you note, this first window is pseudo terminal 0, and we should see some reflection of that. In fact, it reads that this particular pseudo terminal 0 has gedit running and tied to it, and it indicates when the terminal was open at 1552, for example. Whereas pseudo terminal number 1 is running the bash shell, that's this terminal, and we can always tell the terminal by executing TTY, which we've already done, and notice its place in the dev tree, dev PTS, so device pseudo terminal 1. And if we LSL dev PTS, we will see the ones that are currently open, 0, 1, and 2. And notice that they're character devices. We've yet to get into file permissions and file types, but if you see a C as a prefix, it means it's a character type as opposed to a regular file or directory or name pipe or other type of Linux file or Unix file type. So pseudo terminal number 1 has the bash shell running, meaning there isn't another process currently running within that bash shell. And pseudo terminal number 2, at the time W was executed, reflected the fact that the program W was running. Now if we open another shell and execute W, so let's open pseudo terminal number 3 and execute TTY, it's pseudo terminal 3. If we LSL dev PTS, we should see now a newly created entry and its timestamp. And if we execute W, we'll now show that bash is running on pseudo terminal number 2, that's this shell. W is running on pseudo terminal number 3. Now the GNOME terminal allows you to set the title, for example. So for example, we could call this PTS 3, and perhaps this one PTS 2, and switch things up a bit. So these are pseudo terminals, so we can alternate between them to keep track of them. As you close pseudo terminal windows such as PTS 3 and re-execute W, for example, the pseudo terminal is dynamically removed. So now only pseudo terminals 1 and 2 are available. And if we re-enumerate the contents of dev PTS, we see that pseudo terminal number 3 has been removed, as is expected. So these pseudo terminals are created on the fly by your graphical desktop environment manager. And this happens regardless of the graphical desktop environment that you're using, whether it's GNOME, KDE, or otherwise. This is just the way it works. Now, there are a number of other commands that we'd like to discuss, including the W commands. There are a number of these commands, by the way. There are simpler commands which allow you to navigate the Linux file system, such as cd, ls. So cd, for example, changes directory. And this is a command that if you have a background, let's say with DOS, is familiar to you, as DOS derives it from Unix. So to navigate around the Unix tree, Linux tree, you need to use the cd command. It allows us to move from one directory to another directory. But that begs another command. How do we know where we are in the tree? pwd. So pwd prints the working directory. So perhaps even more important is that you know where you are in the tree, pwd, and then use cd to move around. Now, the Linux file system tree is organized with / or root being the root of the tree, the top of the hierarchy, and then directories falling beneath them, as opposed to drive letters over on the Windows side, C:, D:, through whatever colon. So this particular nomenclature allows for basically an infinite number of directories and mount points throughout the hierarchy. So you could have one Linux file system tree that spreads an infinite number of names and depths. So as a consequence, Linux Unix trees can be rather large. Now, with that said, to move around, we simply use cd. Now, something to know about cd, it's hardwired such that when you execute cd with no arguments, it automatically takes you to your home directory. Now, we're currently in our home directory, so it didn't do anything. But let's say we navigated to the root of the file system using cd /. This takes us to the absolute root of the tree. Now, when we execute pwd, we're at the root of the file system. This is the top level in the directory chain. Now, if we notice, the prompt has been updated to reflect that we're at the root as opposed to tilde, which means the user's home directory. Tilde basically is a shortcut or a variable to mean the user's home directory. So from this perspective point, we can change into our home directory simply by executing cd with no arguments. Now notice we're back in our home directory. Tilde is reflected in the prompt to indicate that we're in our home directory. We can navigate levels up, levels down, or where have you. For example, cd /etc, we're now within the etc tree, and cd with no options, we're back to our home directory. pwd always tells you. So you're constantly using, when you administer Linux Unix systems, cd as well as pwd to know where you are. You often reference these commands either by functions within a scripting environment or directly via system call when writing scripts to know where you are and to move around the tree. So cd, pwd are very, very important. Of course, ls. ls is very important because it lists the indicated directory. Now, of course, if you don't specify a directory, it lists the contents of the current directory. So this is the directory tree of home Linux CBT, which includes the following items. Notice that they're colorized in blue. Items that are colorized in blue within the GNOME desktop environment are directories. So these are directories. Now, ls by default does not list in long format, so we don't see attributes or features, characteristics of these directory items. In fact, we don't even see some of the other items that are hidden. There are files and directories that are hidden by default that we do not see by executing ls in this fashion. But nonetheless, ls will show you files that are not hidden and directories that are not hidden, and where appropriate, it'll colorize them. So for example, let's change into etc_init.d, where the scripts that start the system live. When we ls in this directory, notice it's short format in a columnar form, so not long format, and they're all painted or colorized green to indicate that they're executable. So green executable, blue directories. That's the default colorization. Let's navigate back into our home directory, ls again. Now you turn on some options like lsl, and all of a sudden you see the attributes associated with these directory entries. Now they're all directory entries. Notice the first bit that describes the entry reflects a D. D means directory, C means character device, hyphen means regular file. Those are just three of the many types that are available. So LSL is more likely how you're going to use the ls command, because notice it enumerates permissions, number of hard links, user owner, group owner, the size of the entry. Directories tend to be 4096 bytes, and the date and time associated with the object, when it was created, when it was last modified. So LSL is how you're likely to use the ls command, but ls has a number of options. All these commands that we've specified, if you ls, for example, with the help option, will return the myriad supported commands. So here's ls's dump. Now, for example, if we use the lowercase a option, this will reveal hidden files. So notice, in addition to the blue colorized entries, which reflects directories, we see these other items that are prefixed with a dot and painted or colorized black, which indicates 1, that they're files, 2, that they're hidden. Now let's combine ls with la, or lsa with l, and this is a long dump which shows the attributes of the various items, which includes that some of these items are regular files, indicated by the first bit being a hyphen as opposed to a D or a C or otherwise. These are directories, so you have hidden directories like config and SSH, where your keys are stored, and known hosts, and a number of other hidden items. Sans the A option, however, just the items that you're likely, or directory entries that you're likely to interact with often, are displayed. So there are a number of hidden items in every user's home directory that's maintained for the sake of being able to run the system, the GNOME desktop environment, and otherwise. So ls is a very important command. It allows us to do things such as sorting. So you can sort, for example, the content, and you can sort by size. If you run the help and grep sort, you'll see that you can sort, let's say, by size, the content. So you can sort by size. This is a shortcut to sort by file size, for example, and there are long options which allow you to sort by access time and otherwise. That's ls. We're not going to spend too much time. We'll use it in all of these commands in different ways throughout our studies. Another command that you might find useful, since Linux aggregates all these data spread across so many directories that make up the Linux file system tree, you often need to find things. That's where the find command can be quite helpful. So finds content based on criteria, and it searches, of course, the directory tree. So if we wanted to find, let's say, all text files in our home directory, so find the path to search, and it's recursive by default. So // means begin in the current directory and work your way down recursively by default. So find, and let's use the criteria name, and in between single quotes, let's look for all files terminating with text. Now, this does not mean that there aren't other files that are of type text or contain textual data. This simply searches for files that end with txt. So this relies upon, of course, the user naming the file with a terminating suffix of text, for example. So here we see 2 items have been found. Let's just take this dump. Just as that, so quickly, it's able to tell us in our tree what contains text as a suffix. This can be quite useful. So let's just show what we've executed here, and that shows that with this particular criteria, fine, I want to put it between single quotes. Let's use double quotes since single quotes are being used otherwise. So this searches the current directory and below. So searches current directory and below for files terminating with txt. And here it's told us that there's a notes file. That's the file we're currently working on. And another file, URL classifier key 3.txt, that's beneath the Firefox hierarchy. So those are the only 2 items that are of type or end with txt, not of type text, which actually brings up another command, and that is file. File uses a variety of methods to ascertain the content type of a file. This is a very useful command because it uses MIME types, magic files, and a number of mechanisms for determining what's inside of a file. Is it a PDF? Is it an OpenOffice file? Is it some other type of binary for a particular platform? Or is it just plain old ASCII text or HTML or otherwise, or Perl script, Bash script, etc.? So file, followed by the name of the file, identifies the content type of a given file. Very useful utilities. For example, let's look at the items that are here. These are all directories. So if we did file star, notice it even knows that they're directories. So it tells us, even if you didn't recall that blue means directories, file space star enumerating the items that are not hidden, of course, tells us that they're all directories. What about the hidden items? Well, here's some hidden items. For example, what about this accessions error, for example, accession errors? So file dot accession errors tells us that it's an ASCII text file. So this means that programs that are prodigious with ASCII text can be used to use or to peruse the contents of the file at will, such as pagers like less, for example, or more. So if we wanted to examine the contents of this file, we could use less accession errors, and there's a content of accession errors. Or we could cat its contents using yet another program which concatenates textual data, which leads us to listing those two items. So cat concatenates textual content, and less is a pager. So basically it displays textual data one page at a time. So, but of course cat can be used in so many other ways. This is just the tip of the iceberg. So for example, we like to show that if you have content spread across multiple files, you can use cat to combine that content. So for example, let's echo file 1, for example, or let's echo the number 1 into 1.txt. We'll echo 2 into 2.txt. So now we've got these two new files, 1.txt, 2.txt. File star text reveals it. Find the most recent invocation of it shows that there are now two new text files. So the content are split across these two files. Let's cat star text. Now notice, 1 comes from one file, 2 comes from the other file, because that's how we created it. Cat will take content from two files, or from the files that are indicated, however number of files indicated, and dump their output to standard out. So if we cat 1.txt and 2.txt, it simply dumps the output as it reads them. What if we catenated first 2.txt followed by 1.txt, then 2 comes first, then 1 comes second? You can then use a little bit of output redirection to create a combined file. So cat 1.txt space 2.txt into, let's say, 1 through 2.txt, and then cat 2 or 1 through 2.txt, and we see that the content now lives in, or both of the items now live in one file. So cat allows us to concatenate data across multiple files. Of course, we're not restricted to just two files. This is just a simple example of what you can do with a program like cat. So concatenates 1.txt and 2.txt into 1-2.txt. So it's a great way, if you have reams of textual data, to amalgamate them for usage in some other realm, for example. So that's the purpose of using programs like cat. So many other commands to look at. For example, let's create a file using touch. Touch is a program that will create a 0-byte file. So it creates 0-byte file if the file is non-existent, and updates timestamp otherwise. So let's take a look. We've got 1.txt, 2.txt. Let's touch 3.txt, which doesn't exist. Let's LSL. There is our newly created 0-byte file 3.txt. It's empty. It's ready to be written by some other process. Now supposing we populated 3.txt with data. Let's echo 3 into, and we'll use a pen redirection, 3.txt. So now when we cat 3.txt, it contains the number 3. Now when we touch the file 3.txt and re-LSL 3.txt, it's no longer 0 bytes, it's now 2 bytes, and its timestamp has been updated accordingly to match the current timestamp, which leads us to another command, by the way, and that's stat. If we stat 3.txt, we see more information about 3.txt, including the 3 timestamps that are associated with every file. Access modify, and let's just paste this in, and change attributes. So stat is yet another useful command. Stat returns file statistics, which really means attributes. So stat3.text returns this useful information. Now, because our root file system is of type ext3, the time precision is on the order of seconds, not nanoseconds. If we upgraded the file system to ext4 or created a new file system with ext4, then each object that's created will have or reflect nanosecond precision, which is much more useful for time-sensitive applications. So we've looked at so far 14 useful utilities. There are a number of other utilities to look at. So next, we'll look at as many of them as we can, and then we'll continue to use them throughout our studies.